So, before proceeding further, I would like to mention that there was some serious slip, it seems, I am not very sure. It is in application of that transformation from surface integral to volume integral. So, I have written something wrong and you have not pointed out, maybe because of non familiarity with the notation. So, first I will correct that. You know that conversion from surface integral to volume integral is what is commonly called as the divergence theorem, is given by integration of any vector, let us say f, over the surface of any volume is divergence of that vector integrated over that volume. The relationship between this volume and area is, this area is the surface area of this volume. Okay. They are not just any arbitrary area and volume. This volume is enclosed by this surface, or this surface is the surface of this particular volume. So, this is what is the relation and commonly called as divergence theorem or Gauss divergence theorem. This is what is called divergence theorem. Also called Gauss theorem. Now, this is the rule that we applied while evaluating the moment due to the surface forces. Okay. Now, the surface forces were, if you remember, look back to your yesterday's note or last class note, that the surface force, please correct me if I am not using the notations as it was in the last class, epsilon I j k r j T k L N L d A integrated over the surface. This part is all right. Okay. This we are applying this divergence theorem, which resulted or which will result epsilon I j k divergence R j okay. It seems that perhaps while writing this, I wrote N L also on this right hand side. If I wrote N L here, okay, then remove it, because that N L will not be there on this. This comes directly from this relation. Okay. And because of this N L, the divergence here is with respect to this R L. The divergence is written as R L. You can which is the second subscript for T. Okay. So, that is the only correction, that this N L will not be there. The N represents the normal to the surface. So, the right hand side is not surface integral, it is a volume integral. So, there is no question of that N, and that N is being taken care of by this R L. You can see that this has the same subscript what N had, which is again the second subscript of this T k L. Okay. So, that small bit of correction. Anyway, the result what we found that of course, is not changing because of this. I think in this statement it was a slip that I wrote that NL, but the subsequent steps of course, I did not anyway. And the result that we found that the stress tensor is symmetric. Okay. Now, I hope or I think it is correct that you have already come across, if not stress tensor in direct details, but the moment of inertia tensor, that is also another tensor which you have come across earlier. This is a general property of any tensor, that if you change your axis system, particularly if you rotate the axis system, then the element of these tensor will change. Like this stress tensor TKL, it has the component T11, T12, T13 and so on. These components will change if you change your axis system, particularly if you rotate your axis system. And there is a particular axis system, with respect to that all the off diagonal terms, that is T12, T13 and so on, all of them become 0, only the diagonal elements remain. One particular axis system, if you go on rotating, say you have a particular axis system, based on that axis system you have evaluated everything. Think about the moment of inertia, which is simply evaluated as something square of the distance into dm, and of course, the square of, now if you rotate your axis system, these elements will change. At one particular orientation of the axis system, you will find that all off diagonal elements have become 0, only the diagonal elements remain. This particular axis system is called principal axis system. This also I think you have done your earlier mechanics course in connection with stress, principal stresses, principal strains you have found. Now, tensors also have a very important property, which are known as invariants. A second order tensor has 3 invariants. A second order tensor means which are mathematically represented by a 3 by 3 matrix, has 3 invariants. Invariant means which do not vary as we rotate our axis system. They are called invariants, and a second order tensor, that is 3 by 3 tensor, has 3 invariants. So, they are called the tensor invariants. So, we have the tensors have principal axis system, these are certain properties of all tensors. Then tensor invariants, a second order tensor has 3 tensor invariants, 3 invariants for second order tensor. Now, see, the tensors are represented by matrix. Okay. The tensors are usually represented by matrix, but you should remember that there is some difference between a matrix and tensor. Since tensors are represented as matrix, so any type of matrix operation that you can perform on matrix, that can be performed on the tensors also. The main or the basic differences comes from here. The tensor is matrix is just a collection of numbers. Those numbers do not have any meaning. When we call it is a matrix, those numbers do not have any meaning, they are just collection of numbers. However, the tensor is a physical quantity. Tensor is a physical quantity. So, its elements has a very definite meaning, like in this case of stress tensor Tij, as you mentioned that Tij represent the force per unit area along I direction acting on a surface which has j its normal. But if you just write a matrix, then the numbers whatever they are in the matrix, the elements of the matrix, they do not have any other meaning, they are just number. Now, the three tensor invariants, of course, we will be only using the first invariant, not the second and third invariant, but since we have mentioned, we will tell you what are the three invariants. The first invariance is what is called the trace, that is sum of the diagonals. It is invariant. That means, as I said that if you rotate your axis system, the tensor elements will change. There is a particular orientation where no off diagonal elements are there, all off diagonal elements are 0, only the diagonal elements are there. But whatever the change is, the change will be always such that the sum of the diagonal elements will always remain constant. That is, let us say if you have stress tensor, each component is representing force per unit area along a particular direction acting on a particular plane. Those individual component will change if we change on keep on changing our axis system, particularly if we keep on rotating. Okay. However, whatever those individual elements are, the sum of the diagonal will always remain fixed, constant. So, that is the first tensor invariant, the trace of the tensor or trace of the matrix representing that particular tensor is always constant. That is, first is the trace usually denoted by TR, trace of T I j is constant. That is, the trace of T I j is what? T I I. When I write T I I, this index I is repeating. So, it means T 11 plus T 22 plus T 33. Okay. This is constant. T 11, T 22, T 33, all three of them can change, but will change in such a way that the sum will remain constant. The second tensor invariant is that sum of the principal minors is constant, which in this case can be written as, say, the second invariant. Let us denote these diagonal elements only, or let us think about this T matrix T 11 into T 22 plus T 22 into T 33 plus T 33 into T 11 minus T 12 square minus T 23 square minus T 31 square is constant. This is true for any tensor, not only that stress tensor, any other tensor like say moment of inertia tensor or strain tensor or any other tensor which you may come across. It is true for all of them. Whenever is a second order tensor, there are three invariants, and these are, and the third is determinant of the matrix formed by T I j. How do you write? Say T we have already used for force. So, determinant of, let us simply call it determinant instead of writing by any notation, because we are not going to use it. Determinant of the matrix is also constant. This is the third invariant. So, if you have any tensor, these are the three invariants of the tensor. So, when we rotate the axis system, so that the elements of this matrix or the individual stress elements are changing, but the change is such that the sum of the diagonal always remain constant. Now, what are these diagonal elements? If you look to this matrix, or let us write the in a matrix form, the stress tensor in the matrix form. The stress tensor, if we write in matrix form, is T11, T12, T13, T21, which is same as T12. Okay. So, we are not going to write it T21, but we will write as T12, T22, T23, T31 is same as again T13 because of symmetry. So, we will again write T13, T32 is again same as 23 and T33. Now, T11 is the force per unit area acting along direction 1 on a surface to which direction 1 is normal. Now, think about say in terms of x, y, z, because that might be little more comfortable to you. That is, if we think it is T x x, then it is x component of the force per unit area, of course, acting on a face which is normal to x. So, what is this force? This is a force normal to that plane. So, these all these diagonal components, they represent normal stresses, the stress which is normal to the face on which it is acting. The others are T12, we can say very easy, it might be easier to comprehend using a 2-dimensional element. In a 2 dimension, an element is simply say a simple rectangle. We will make a smaller rectangle instead of making such a big rectangle. Let us say this for your convenience, we shade it x y. So, the T x x will be in this direction acting on this face, this because x is normal to this face, also to this face. The direction it might be along this or along this. We are not worried about the direction at this stage, whether it is towards the face or away from the face, but this is normal to the face. What about T12? You can see that that will be something like this. Okay. So, if we call this T11, this x is 1, y is 2. Now, so these off diagonal elements are all tangential stress, also commonly called as shear stress, and the diagonal terms are the normal stress, and you know that normal stresses are either tension or compression. The normal stresses are either tension or compression, and the off diagonal elements are also at tangential stress or shear stress. So, diagonal elements they represent normal stress, off diagonal elements tangential stress or shear stress. Now, with this we will see what is the meaning of the definition that we initially proposed for our fluids. We defined fluid are substances which cannot withstand any tendency by applied forces to deform it in such a way that leaves the volume unchanged. Or other way, that if we apply a force then fluids are those substances which will not be able to the tendency of this force to deform it without changing the volume. That means, it can withstand, but in that process it has to change its volume. Without changing the volume, it cannot deform. No such deformation is possible which will leave its volume unchanged. When a force is applied, okay, it will deform, all right, but the deformation will be such that the volume will not remain unchanged, the volume has to change. That is the definition we proposed for fluid, and we will see what is the meaning of that in terms of this stress. For that, first of all, we will consider this fluid is at rest. Okay. Let us consider fluid at rest, and for simplicity, so we will call stress tensor. We would like to see how the stress tensor is for fluid at rest. For convenience, let us consider a spherical element. Consider a spherical element. Sufficiently small, okay. This fluid element is sufficiently small, so that we can consider the stress tensor is more or less uniform. You can assume, we will later on see what it is, but we will assume that a small fluid element, spherical element, so that the stress tensor remain more or less uniform, and we will choose the principal axis system for stress. Okay. That we can choose without losing any generality, that we are choosing only the principal set of axis, set of principal axis system. So, that the stress tensor contain only diagonal element. Okay. So, consider again principal axis system. So, the stress tensor is what we have already know, that we have written all T11 0 0 0 T22 0 0 0 T33, and to make that this is principal system and different from the other, let us denote a prime. Okay. That these are now the principal stresses. However, we know that this is an invariant Tii equal to constant. Once again Tii means T11 plus T2 plus T33, and that is constant means the same is T11 prime plus T2 prime plus T33 prime. Okay. So, this implies that for any condition T11 plus T22 plus T33 equal to T11 prime plus T22 prime plus T33 prime. Okay. Now, we would like to write this stress as sum of two stress tensor, that is, we would like to write, let us write it explicitly instead of using any notation. This is simple. So, if we say that this is the stress that is acting on the fluid, we can say that means these two stresses are acting on it, in which in one case we have made it 1/3 of the sum, and the whatever is left out, that we have to consider as a second stress system. Now, look to this first stress system, what it is. This is equal in all direction. This has a spherical symmetry or isotropic behavior, equal in all direction. And since all are same, this means that all three are either tension or compression. As it happens, it is actually compression. That is what fluid can take at rest. It cannot take tension. Anyway, so but all three are same. Our experience says that this is compression, that all three are compression. Now, what happens if that type of stress is applied on a fluid element, a spherical element in which an isotropic compression is applied, equal amount of compression in all direction? Its volume will change. In case of compression, it will be compressed, volume will decrease. Fine. So, this deformation resulting in change in volume. So, according to our definition, this is permitted. That is, an isotropic state of compression is allowed. Our definition of fluid permits it. Now, look to the second one. We will call it, say this, denote it, say 1 and 2. So, 1 represent isotropic, we are calling it compression from our so this is deformation with change in volume, deform it which is permissible by, so satisfies the definition. Satisfies the definition of fluid that we have proposed. Now, look to the second one. The sum of this diagonal or the stress of this matrix is 0. If you sum the diagonal, it becomes 0. Then what does it mean? All three are normal stresses and sum of the normal stresses are 0. Obviously, it implies that at least one is tension and at least one is compression. The third one may be either tension or compression. All three cannot be same. At least one is tension, at least one is compression, and the third one might be either of the two, so that the sum becomes 0. Now, if this type of force is applied on a spherical element, what will happen? In one axis, along one axis you are applying a tension, along another axis you are applying a compression, and along the third axis you are applying either a tension or compression, such that the sum total of this tension and compression is 0. Yes, volume will not change, because the sum total of the compression and tension is 0. So, the total volume will remain unchanged, but as far as deformation will occur. What type of shape the sphere will become? Ellipsoid. A sphere will not become cylindrical, it will become ellipsoid. You have stresses from all three directions. So, this second part imposes that the deformation will be such that there will be no change in volume, and our definition of fluid does not permit that, meaning that the second part of the stress will not be possible, that will not exist in a fluid at rest. So, write the second part, sum of diagonals or sum of normal stress, the result sum of normal stress is 0, no change in volume, at least one is compression, at least one is tension, the third is either of the two. So, deformation is sphere to ellipsoid. Deformation without change in volume. So, not allowed by the definition that we have. So, what is the meaning of this then? That when a fluid is at rest, the stress system has to be isotropic, equal in all direction, and as it happens this is compression, and it is all axis system or principal axis system. All axis system are principal axis system. For a fluid at rest, all axis system are principal axis of stress, and at any point the stress is only isotropic compression, that is equal from all side, a compression equal from all side, from all direction, and all directions are principal direction. As it happens, this isotropic stress is compression. A fluid at rest cannot take tension. So, for fluid at rest, stress is isotropic in nature, only normal stresses act, all axes are principal axis of stress, and we can write the stress system, the stress tensor and in the second term delta ij is written to make it a mathematically compatible equation, because 1/3 T I I is just a number. This T I j represent a tensor, but 1/3 T I I is just a number, 1/3 of T 11 plus T 22 plus T 33. So, this delta I j is given, so that it has the tensor form, and this 1/3 T I I, since it is equal in all direction, we do not need to write all the time T I I and all, we can just write one number which we have written here P, and call this as fluid static pressure. Perhaps the word hydrostatic pressure is more familiar to you, because say water was perhaps the most common fluid or studied most, the fluid that has been studied most, and pressure and all these things were usually encountered with water. So, since long this pressure is referred to usually as hydrostatic pressure, but we are making it more general, fluid static pressure. So, this is the definition then of static fluid pressure, that it is 1/3 of the sum of the normal stresses acting on a fluid at rest. I think you have come across another definition of pressure in your thermodynamics. I do not know whether you had a formal course on thermodynamics or not, but you might have a course on kinetic theory in school physics, and in that context you defined something called pressure, coming because of the collision and momentum transport. Okay, may not be in that details, but because of that collisions, the so called properties of the substance, or in that case perhaps you studied only gas, which is also fluid. So, properties of fluid, particularly the pressure and temperature, all are basically manifestation of those molecular motion and their collision. So, that is the thermodynamic pressure. This we have got something based on a stress consideration, or let us say dynamic or mechanics consideration. So, this is, that is a thermodynamic pressure, this is a mechanical pressure. Is there any relationship between the two? Okay, we will not answer that question now, we will leave it for later, but we will later on come at what is the difference between this pressure and that pressure, or is there at all any difference, or both are same, but this of course we will discuss little later. So, now the definition of that fluid that we initially postulated has become clear, that what we intended as a definition of the fluid is that the stress system for fluid at rest must be only an isotropic compression, and that is what is the implication of that definition, that fluid while at rest takes only an isotropic compression. Now, let us move on to the equilibrium. We have already discussed that two forces are acting in general on a fluid at bulk. If we consider a certain bulk amount of fluid, there are two forces acting on it, and when the fluid is at rest, of course, these two forces must balance each other, the body force and the surface force. So, say for fluid at rest in equilibrium, or equilibrium consideration of, because at rest is has to be in equilibrium. So, that is actually superfluous when you say fluid at rest in equilibrium, at rest has to be in equilibrium. So, we are considering now equilibrium condition. Now, the forces acting, the body force, how much is the total body force? Consider a fluid of volume V, which is bounded by a surface, then what is the total body force acting on it? Total body force is, we have already defined the body force to be rho f dV. So, when this is integrated over the entire volume, this gives the total body force. Let us call this to be capital F, and it is if you want, you can use even this vector notation, otherwise you can forget. And the total surface force acting on the same fluid, total surface force acting on the same fluid, how much it is? Yes. Now, it should be straightforward to write that. Earlier we have written it already, tau I j n j d a, but now tau I j n j has a special meaning. The tau I j we have got a definite value. Yes. The tau I j has become minus p. The tau I j has become now minus p. So, you can simply write that p. Integrated over the surface which encloses this volume V, and again we can apply this divergence theorem, because these you need to equate, we need to balance. So, they should be of same type of quantity. So, this becomes in terms of volume integral what it is? And since the fluid is at rest, the sum of these two forces is 0. remember there is something about the volume, this V. This surface or this volume, since we are considering in the first relation itself, the total body force is V integrated over this volume. That means, this volume must be entirely within the fluid. You cannot consider a volume which is partly in fluid and partly not. The volume must be such that it is entirely within the fluid. And since this relation is general for any arbitrary volume, we can say that the integrand itself is 0. So, that is or to give our notation, this f is a vector. So, we will write in vector notation rho f I this is plus and as you know that the body force is often the gravitational force, that is this F is g, and you can have your axis system aligned in such a way that the g has only one component. In that case, see, this is actually representing 3 small differential equation. For each I equal to 1, 2, 3, it represent 3 small differential equation dp dx 1 equal to rho f 1 and so on. And you can choose your axis system, particularly when the body force is simply gravitational force, and you know it is only in one direction. So, you can make align your axis along with that. So, that only one equation will have a non-zero right hand side, the other 2 equations will have 0 right hand side. Now, for those cases where the body force F is a potential function or conservative force field, let us say for conservative force field, let us write this or your where psi is what? The potential energy per unit mass, the potential function, is not it? The potential energy associated, potential energy per unit mass associated with this conservative field. And if we put it here, then what do we get? For conservative force field, the equation then become okay, write this gradient notation. If we take a curl of this, you are familiar with the operator curl. So, if we take a curl of it, what will be the result? if we take the curl of it, what will be the result? Curl of a gradient, curl of a gradient is always 0, curl of a gradient is always 0. The curl usually written in this fashion, the minus of course we can take it. And this further becomes now see, starting from this equation, if we start from this equation indicates that there will be certain surfaces on which the pressure will remain same. If we consider a fluid under different condition, then there will be certain surfaces on which the pressure will remain constant, and so will be density. These surfaces we may call it level surface, because the pressure is same on that. So, there are level surfaces for pressure, similarly level surfaces for density, and also level surfaces for psi. Psi, as we mentioned, that this psi function represents potential energy per unit mass associated with this this force field. Again, you know that on us there are surfaces on which the potential energy is fixed, like if you think in terms of the gravitational potential, which is measured from the center of the earth. So, at any fixed altitude the potential energy will remain same, which is not exactly a horizontal surface. If you think in terms of the earth, it is a spherical surface. So, similarly, there are level surface for pressure, there are level surface of density, and there are level surface for potential energy. And looking to the last equation, this curl gradient of rho cross gradient of psi equal to 0, what does it mean? Gradient, the result of gradient operator is always a vector. So, gradient of rho is a vector, gradient of psi is a vector. So, this two cross product of two vector is 0. What is that? So, that means this says that level surface of density and level surface of this potential energy, they will coincide. The last relation has the meaning that the level surface of density and level surface of this gravitational or the potential energy will coincide. Also, the first relation or the first relation on this page, this gives one more information, that the level surface of pressure is normal to the direction of the body force. Level surface of pressure is normal to the body force. That comes from this equation. Level surface of pressure is normal to the body force.